So we're going to take a look at some periodic trends we see with the elements and what the cause of those trends are. And those are going to be related to orbital energies and things going on with the electrons in an atom. First thing we need to get down, we need an understanding of what valence electrons are. Remember, valence electrons are going to be electrons in the subshells of the highest principal energy shell. Okay, so when we do electron configuration, the electrons that have the highest n value, those are going to be our valence electrons. Versus our core electrons, which are going to be the electrons in those lower energy shells. Typically, when we do a noble gas core configuration, the noble gas core, that's the core electrons. Any electrons outside that are going to be valence electrons. Now, we need to know about valence electrons. We need to know about core electrons. We also need to know something called nuclear charge. We're going to discuss the effect of nuclear charge on these electrons and on these energy levels. So, nuclear charge is represented by Z. Z is going to be the number of protons in a nucleus. All right, if we think about that, number of protons in a nucleus is going to give us our positive charge in our atom. So the higher that nuclear charge, we're going to get a lower orbital energy because we're going to get a more positive attraction on those electrons. Okay, those electrons are going to be pulled closer towards the nucleus into lower energy levels, and that's going to help stabilize the system. Okay, so let's look at an example of this. If I have a hydrogen atom versus a helium ion, hydrogen has one electron, has one proton. Okay, that electron is at a less stable orbital energy, meaning it's going to be easier to remove. Okay, it's technically at a higher energy level, which means removing it from that hydrogen is going to be easy. So it goes to form H+. Now, that's because the proton, the one proton, has an attractive force on that one electron. So we get that nice attractive force. If I take two electrons and put them in the nucleus, but still only keep that one electron, well, now that one electron feels a +2 pull on it, which makes it harder to remove. So that electron in the helium +1 ion gets pulled closer to the nucleus, okay, because it feels more of a positive attractive force. So we have to worry about the number of protons in the nucleus and their effect, their positive charge effect on the electrons surrounding it in those orbitals. Another thing, though, that we have to look at, we can't just take into account the effects of the nucleus. We also have to worry about effects of other electrons. We have to worry about something called shielding. So if I've got a nucleus with a +3 charge, it's got 3 protons, that means it's a lithium atom. Right? I've got 3 electrons. Well, if I have lithium, its configuration is 1s2, 2s1. So those 1s2 electrons are core electrons. The 2s1 is going to be a valence electrons. Now what happens is those core electrons are going to actually shield those valence electrons from feeling the full effects of the charge of the nucleus. Okay, so because those electrons have a negative charge, they're feeling the attractive force of the nucleus, but they're also going to block off some of that pull to that outermost electron, to those valence electrons. That's something called shielding. That outermost valence electron is being shielded from the nucleus by those core electrons. In this picture here, dealing with shielding, what that means is we get a net overall charge of about 1+ on that electron. Basically, the positive charge minus the number of electrons in the core, basically the positive charge in the nucleus minus the number of electrons shielding that electron, so +3 minus 2 gives me an overall charge of +1. So outermost electron feels a charge of +1. If somehow that outermost electron could penetrate into that electron cloud where those 2 electrons are, it would no longer be shielded, it'd feel a full +3 charge attraction. Okay, so we have to worry about this shielding because that's going to be very important when dealing with periodic trends. So with that shielding, we can actually calculate something called Z effective, which is going to be the effective nuclear charge. To calculate that, we're going to take Z, which is the number of protons in the nucleus, minus S, which is the number of electrons between the nucleus and the electron of interest. So that S is going to be calculated by looking at the additional electrons in the inner orbitals, or the core electrons. Those inner electrons are going to shield the outer electrons more effectively than electrons in the same sublevel. So for example, let's say I had chlorine. Chlorine would be neon 3s2 3p5. What this is saying is those core electrons in the neon are going to shield those outermost electrons, the 3s2 3p5, more effectively than, say, the 3s electrons shield the 3p electrons. Okay? Mainly, Z is the number of protons in the nucleus. S is going to be the core electrons if you want to look at Z effective on those outermost valence electrons. So if I look at the top picture here with lithium, right, lithium's got a +3 charge. It's got 1s2, 2s1. So those 1s electrons are going to basically shield or block that 2s electron from feeling the full +3 charge. So to calculate Z effective on that 2s electron, we'd take a +3 minus 2, because we've got 2 electrons shielding it, to get an overall +1 charge. So that 2s1 electron has got a +1 charge as far as its Z effective goes. So it feels a +1 attraction. Now if I look at Z effective for the 1s electrons themselves, well, that would be a +3 minus, well, S in that case would be 0, right? Because we have no electrons between the 1s electrons and the nucleus. So Z effective on those 1s electrons would be a +3 because they aren't shielded from the nucleus at all. Okay, so the 2s electrons would feel a charge of +1. The 1s electrons would feel a charge of +3. Now because of that shielding though, those 2s electrons end up going to a higher energy level, which means it's going to be less stable, which means it's going to be easier to remove that electron. So that's why lithium will form a +1. If I were to take away those shielding electrons and not have anything, let's say I could remove the 1s electrons, well, then it would be a +3 minus 0. When that 2s1 electron would feel a +3 attractive force. Because it felt a +3 attractive force, it would be pulled in closer to the nucleus. It would have a stronger attractive force on it. Therefore, it would be at a lower energy, and it would be harder to remove that electron because it's now feeling a more attractive force. All right, so keep that in mind with Z effective. We're going to take the nuclear charge minus the number of electrons, or you could look at it as the nuclear charge plus the charge of the electrons. Knowing that effect of a nuclear charge is going to help us predict a lot of different properties from the periodic table. Okay, the other thing, don't forget those electron configurations so that you know what the core electrons are, what the valence electrons are. So Z effective is going to affect orbital energy levels. So different atoms are going to have slightly different orbital energy levels. Now another thing that we need to think about when we're thinking about the Z effective and the effects of electrons, we have to think about additional electrons in the same orbital. If we have an additional electron in the same orbital, that's going to raise the orbital energy because we're going to have electron-electron repulsion. So if I look at helium, I've got a +2 charge. I've got 2 electrons in the neutral atom of helium. So each one of those electrons feels a Z effective of +2. But now, as those electrons are pulled closer and closer in, they get closer and closer together. Well, their negative charge repels each other. So because of that, we get that attractive force, we get that repulsion force. So because we have that extra electron, that repulsive force moves it to a higher energy level, making it easier to remove one of those electrons. Because it's in a less stable state, it's at a higher energy level. Now, if we remove one of those electrons, now all we have left is just that attractive force between the nucleus and the electron. That's it. That's all we have left. So we don't have that repulsive force anymore. So that helps stabilize this ion. Okay, so we have to worry about Z effective. We have to worry about the number of protons in the nucleus and shielding by electrons in the core. We then also have to worry about those repulsive forces by electrons in the same energy levels. All right, so keep those factors in mind when we start talking about these periodic trends. So let's look at these atomic sizes. As we go down a group, the radius of an atom, the size of an atom is going to increase. Well, why is it going to increase as we go down a group? Well, right off the bat, we're adding more electrons, so it's going to occupy more space just because we have more and more electrons. Now, to go along with that, too, if we have more inner electrons, we're going to get more shielding. If we have more shielding, we're going to get less attractive force, those electrons are going to repel each other a lot more, so we're going to get a larger atom. So as we go down a group, radius increases. Those are the factors that cause that. All right. As we go across a period, radius is going to decrease. Why? Well, Z effective is going to increase across the period. So as we go across a row, the number of core electrons don't change, but the number of protons in the nucleus do. Because of that, we get a larger Z value, the same S value, which means our Z effective then is going to get larger. Larger Z effective means we have a more of attractive force, which pulls those electrons closer towards the nucleus, which makes a smaller atomic size. Okay, so keep those trends in mind. I'm going to increase size as I go down a group, and I'm going to increase in size as I go from the right-hand side of the periodic table to the left-hand side of the periodic table. Okay, so just looking at these atoms here, you can see relative sizes of those. So if I look at group 1, as I go from hydrogen down to francium, I get a larger atomic size. Why? Putting more electrons in, I'm also getting more inner electrons, more shielding, less attractive force. They expand more, they get bigger. If I go from lithium across over to neon, as I go from lithium to neon, I get a smaller radius, smaller atomic size. Why? Well, all of those have the same noble gas core configuration, right? They all have helium as the noble gas core configuration, which means all of those have 2 inner electrons. So they only have 2 electrons shielding them, but as I go from lithium to neon, lithium has 3 protons, neon has 10 protons. So my Z effective for lithium would be 3 minus 2, so a plus 1. My Z effective for neon would be 10 minus 2, or a plus 8. So the electrons in lithium feel a plus 1 charge. The electrons in neon feel a plus 8 charge. Well, that plus 8 pulls those electrons closer towards it, which results in a smaller radius. Now, if you look at the blue boxes on the bottom, those are the transition metals. Now, again, when looking at this stuff, transition metals are going to be an exception. Okay, so if you look at those transition metals, they don't really change much in atomic size. They keep a constant atomic size. And that's typically because their outermost valence electrons are going to be those s electrons. So they technically all have the same outermost valence electrons. Those d electrons are really going to be considered kind of core electrons. So as we add more Z value, in other words, we add more protons in, well, we're also adding equal number of inner electrons. So everything seems about the same because that Z effective doesn't change that much across that. So those were the neutral atoms. Let's look at ions formed from those neutral atoms. So if we're going to take electrons away, we're going to get a cation. So with a cation, we're going to end up with a smaller radius than the neutral atom. Why? Well, we have the same Z effective, but now we have fewer outer electrons, so we get less of that repulsive force, and so those electrons are able to be pulled in closer. We haven't changed the number of core electrons, we haven't changed the number of protons. All we've done is taken some of those valence electrons away. So with those valence electrons gone, less repulsive force between those valence electrons, which results in a lowering of energy, which means a smaller radius. All right, if I add electrons, I'm going to get an anion formed, and I'm going to end up with a larger radius. This is going to be the opposite reason of the cation. Still going to have the same Z effective, but now with more electrons in our outermost shell. More electrons means more repulsion. They're going to push further away from each other in that outermost shell. And so I'm going to get a larger radius. So if I look at the trends here, cation side, the blue is the neutral atom, the gray is their ion. Anion side on the right, the pink is the neutral atom, the gray is the anion. If I look at sodium, sodium starts with a radius of 186. When I take that one electron away, the radius becomes 102. Why? Well, because I have fewer valence electrons, therefore I get less repulsive forces. They get it closer and closer together. Same thing goes with magnesium. If I go to form magnesium 2+, from neutral magnesium, I get a smaller radius because I lose that repulsive forces from the valence electrons. Okay, when I go to the anions over on the right, when I add electrons, when I add an extra electron to go to a negative charge, my radius increases. Right? So if I look at fluorine, Neutral atom for fluorine is a 72 radius. If I go to F minus, I get 133. Why? Well, when I add that extra electron, those electrons in the valence shell in the fluorine now get more repulsive forces, and they spread apart more to give me that larger ionic radius. Okay, so cations are going to form smaller radius, anions are going to form larger radius. The atomic radii rules still apply here too, though. As I go down a group, it gets bigger. All right, this is just a little bit prettier picture to see that. So you can see their ions and their charges and their relative sizes. Okay, so we've looked at atomic radius, we've looked at ionic radius. These are some periodic trends, and things that are grouped in the same column in a periodic table show similar trends.